In this video, I'll be discussing the system design of an online auction portal. We'll see how the auctions are generated for an item, how users can place a bid, how do we see the latest status of the auction, like who placed the latest bid, what was the latest bid amount. We'll try to come up with a scalable and fault-tolerant architecture here.
Now let's start with the functional and non-functional requirements. Functional requirements, the first one is users can add items for auction, users can bid on items, users can view highest bid for an auction, closing an auction based on a closing time or 10 minutes after last bid. Non-functional requirements. So first thing is the system should be highly available. Next, concurrent bids. So the placing a bid operation is highly concurrent. The write contention is very high. Placing a bid is also consistent. That means immediate visibility is needed and can't lose bids. So immediately after a bid is placed, that should be visible to all the other users. Scalable for viral auctions. So we need to design the system in such a way that it is scalable for viral auctions. Real-time view of bids update. So every time a bid is placed, the other user should view the latest bid in real time. System is read heavy. So yes, the placing a bid is a highly concurrent operation, but still the system is actually read heavy. So there will be more reads than the writes. So we need to show the latest bids, auction status, time left for one auction. Next, I will discuss about the high level design. So here we have this auction service, and these are the user operations. User can create auctions, place a bid, and also can view the auction status. So here we have the auction database. Service is writing to this auction database. So we have auction table, bids table, and the users table. So for auction, we have the auction ID, seller ID, item ID, start time, closing type. Closing type can be either based on some closing time or dynamic. Like after the last bid, we'll wait for 10 minutes and then we'll close the auction. Closing time, start price, winning bid, winner, and created timestamp. For bids, we are having bid ID, auction ID, user ID, price, and timestamp. So we are not just storing the latest bid or the current bid, we are storing all the bids for all the users, because we, for auditing purpose or for analytics purpose, we are going ahead with this event sourcing based approach. For users table, we'll have the user ID and other metadata like name, email, contact, or other informations. Now, one quick thing here is how do we close the auctions or end the auction? So based on this closing type or end type. So if it is based on a particular time, so we can schedule a job to end the auction at that time. Otherwise, if it is dynamic, so then we can periodically run a job, let's say in every minute or in every 2 minutes, and it will look for auctions for which the latest bid happened before 10 minutes, right? Those auctions it can end. Now, this is the auction service. This is the black box here, which I'll be breaking into pieces. One thing is we are designing a large scale system, and we have seen the scale for different operations. We have different scales. So we need to go for a microservice based architecture, and we'll have multiple services for different operations, and each service will be scaled separately. So now this is the modified architecture here. So here we have this auction create service. This is to create auction. This is the bid service. This is for placing a bid, and this is the view service for viewing the or getting the auction status. So here we are using this API gateway. API gateway is responsible for authentication, authorization, load balancing, API routing, rate limiting, etc. Now, this is the auction DB. Here we have the auction table, and here is we have the bids table. Now, first I'll be discussing about placing a bid. So we have already discussed that placing a bid is a very concurrent operations. So how do we handle the high contention? So there are lots of concurrent bid updates are happening. So we need to improve our bid service to handle high throughput. We have to make it very fast. So for that, we can introduce one queue before the bid service. So basically, we are making the bid placing flow asynchronous. We can horizontally scale this bid service and read from the queue. So we are having this lambdas, or we can have API servers. The responsibility for this is just to take the bid placing request and uh, put it in the queue. And this bid placing service will be scaled, and it will listen from this queue. And it will have some logic in this bid service whether to accept the bid or not, and then it will store it in the database. Now, how do we maintain the bid order sequence? Because we have to maintain or preserve the bid order sequence. In the order bids have come to our system. So for that, we can consider the Kafka sequence, the sequence in which the request have inserted in the queue. That sequence only we can consider. Now we all know that Kafka has high write throughput and it is highly scalable. So this is perfect for our solution. We can partition Kafka by auction ID and one consumer per auction. So in this configuration, we will not have any risk conditions. Now with this solution, we have improved the bid ingestion flow. But still, in the bid service, we have to perform some logic to verify whether the received bid from this queue is a valid one or not. And how do we check that? What is the bid acceptance logic? The bid price should be higher than the current highest price. And how do we check that? For the auction ID, we'll check the latest bid and we'll see the price and we'll compare based on that. So this part is still slow because we are checking from the database. So what if this delay in bid processing is not accepted, and if we want faster bid placement? What we can do is we can store the data in the cache, and we don't, in the bid tables we are storing all the bids, right? All the bids with the user ID and timestamp. In the cache we don't need to store everything. In the cache we can just store the auction ID, last bid price, last bidder and end time, because just using the last bid price and last bidder only, or maybe basically just using the last bid price only will verify whether the received bid is valid or not, right? So let's see if we can store this informations in the cache. So consider 8 bytes for each of this field, approximately 32 bytes. If we have 1 million auctions per day, so that means 10 power 6 into 32 bytes. So that is 32 megabyte. So this can easily fit in memory or cache. So this is the amount of data we have to store per day in a cache, which is pretty doable. And we'll verify the bid used from the cache. So now this is the redefined solution here. So the bid service anyway is reading from this queue, bid ingestion queue, and the latest bid for any auction is stored in the cache. Auction ID, last bid price, last bidder. And bid service will compare the received bid with this information in the cache, and it will verify whether to accept the bid or not. And this cache is not persistent, right? We have to update the bids in the database as well. For that, bit service will put this in this Kafka topic, and there will be lots of workers that will listen from this topic and put it in this bits database. Now with this we have optimized our bit placing flow. Next we are considering viewing auction status. So every time a bid is placed, all other users should see the latest bid. Basically, every bid has to be broadcasted to all other users. Now, there are different ways client can fetch the latest bid information for an auction. First one is polling. Client can poll periodically. So the problem here is that client has to poll periodically, right? Again and again, it has to poll for the latest bid information. SSE or server side events. So this is good for our use case because server side events is basically for unidirectional communication from server to client, right? Here in our case, the latest bid information server has to send to client. So for one-sided communication, and this is good for our use case. WebSocket. For WebSocket, will create a bi-directional connection between client and server. So client can send information to server can send message to client, right? It's both way. So we don't need this here because we only have to send information from server to client. But you see, the WebSocket has lower latency than SSE or server-side events. So just because of that, I have considered WebSocket here for our design. So this is the improved design we have. So bit service is receiving the bits from this queue, and it is sending it to this Redis PubSub. And there are lots of WebSocket servers. Clients are connected to one of these WebSocket servers. Now, after receiving a latest bit from the bit service, Redis PubSub will broadcast the bit to WebSocket servers. And WebSocket server then will send the latest bit information to the clients. So this is the flow. Now, why to use a Redis PubSub here? Redis PubSub offers real-time broadcast to many users. Extremely low latency, sub-millisecond latency we have for Redis PubSub. Scales with multiple WebSocket or SSE servers. When a message is published, all nodes receive it and push it to their respective clients. It's simple and lightweight. The problem with Redis PubSub is fire and forget. So there is no message persistence. So if a subscriber is disconnected, suppose one client is disconnected, the client will miss the message. Now let's see one example here. So let's say we have one auction with ID auction 123. For each auction, we'll be having separate channel in this PubSub. Now client connects to the WebSocket server and joins this auction 123 channel. WebSocket server subscribes to this Redis channel auction 123. So client will connect to this WebSocket server for the auction 123. So auction 123 will have one channel in this Redis PubSub where this WebSocket server will subscribe to this channel. Now, when a new bid is placed, bid service publishes it to Redis. So, publish this auction 123 channel, this is the bid event. So, Redis pushes this message to all subscribed WebSocket servers. So, it will come, bid service will send the bid event for this auction 123 in this Redis PubSub in that channel, and from that channel, whichever servers are subscribed to that channel, all the servers will receive that bid events. Now our WebSocket server then receives the message and forwards it to the connected clients via WebSocket. So again, after getting, WebSocket server will send the message to the client. So this is the whole flow here. Now I have some mapping here to understand how this is working. So consider this is the list of WebSocket servers. This is the first WebSocket server 1, WebSocket server 1. So it has connection for all these auctions, auction 101 and auction 102. For this auction 101, this is the Redis channel, auction channel 101, and these are the clients connected for this auction, C1 and C2. For auction 102, client C3 is connected. In this WebSocket server 2, we have only one auction, auction 101. Redis channel is auction channel 101, and only client C4 is connected to this WebSocket server for this auction. So this is for mapping from here to here, from client to WebSocket server, and for the channel. Now, when the latest bid is coming to Redis PubSub, it is coming to one channel, and we need to know like which all WebSocket servers are connected for that channel. So from channel to WebSocket server mapping also we need. So there is this mapping. Let's say Redis channels. This is the auction channel 101 and auction channel 102. For auction channel 101, we have these two servers, WS server 1, WS server 2. For auction channel 102, only one server is connected or subscribed, that is WS server 1. So if you see, only for WS server 1, we have this auction 102 channel subscribed. So this is just a sample mapping. We can store this mapping in Redis. Also, we can use a zookeeper because we are having a large scale system. We can use a zookeeper for this configurations. So just to give some idea, this is just some example here. Now let's see what all requirements we have made. So we had this functional requirements, adding items for auction, placing bid, seeing the highest bid for auction, and closing an auction. All these functional requirements we have satisfied. Non-functional requirement, the system is highly available. Concurrent bids we have handled. Placing a bid is consistent. Immediate visibility, can't lose bids we have handled. Scalable for viral auctions. Real-time view of bids update, fine. As system is read heavy, we have to show the latest bids, auction status, time left, etc. So I will just discuss about this highly available and scalable part here in our latest design. So if you see these services, all these services are auto scaled. So based on the scale, it will if we are using any cloud-based solutions, all these services will be auto scaled. Here this lambda is stateless, but this Kafka queue, this will be partitioned by the auction ID, and this bid service also will be scaled by auction ID. Is basically one bid consumer will be listening to one partition only. The database we can shard properly. The auction DB can be sharded based on auction ID. Bids DB also can be sharded based on auction ID. And this Kafka, this is highly scalable and highly available, and Redis also is highly scalable and available. So our system is very highly available and scalable. So this is the end of our system design discussion here.